Part 4. Dietary lipids as structural inputs. Chapter 12. What dietary fat becomes. Dietary fat enters the body as a structural input that is broken down, transported, and reassembled into membranes, signaling molecules and energy substrates. It does not remain in its original form, and it is not handled as a uniform fuel. The system deconstructs dietary lipids into components that can be selectively routed based on structural demand. Fatty acids, glycerol backbones, and associated molecules are absorbed, repackaged, and distributed through a transport network that delivers them to tissues where they are either incorporated into membranes or stored for later use. What dietary fat becomes is determined by how these components are allocated across structural and functional pathways. Digestion reduces dietary fat into absorbable units that can cross the intestinal boundary. This process depends on bile and enzymes that interact with lipids within the lumen, converting them into forms that can enter intestinal cells. Once inside, these components are reassembled into transport structures that move through the lymphatic system and into circulation. This initial transformation separates intake from function. The fat that enters the bloodstream has already been reorganized into a form suitable for distribution, not direct use. Transport through circulation directs these lipids to tissues based on demand. Cells take up fatty acids through mechanisms that depend on membrane structure and signaling state. Uptake is not uniform across all tissues. It reflects local conditions such as energy requirements, membrane turnover, and signaling needs. Once inside the cell, fatty acids are partitioned between storage, oxidation, and incorporation into structural components. This partitioning determines whether dietary fat contributes to immediate energy production or to longer-term changes in membrane composition. Incorporation into membranes represents one of the primary fates of dietary fat. Fatty acids become part of phospholipids and other structural lipids that define membrane properties. The types of fatty acids available influence how membranes are built, affecting packing density, fluidity, and permeability. Over time, repeated incorporation shifts membrane composition, altering how cells behave. This is not a rapid process. It reflects cumulative input, where dietary fat gradually changes the structural characteristics of the system. Fatty acids also serve as precursors for signaling molecules. When membranes are remodeled or broken down, these fatty acids can be converted into compounds that influence inflammation, vascular behavior, and cellular communication. The signaling profile that emerges depends on the composition of the membrane, linking dietary input to downstream signaling capacity. This connection is indirect but persistent, as membrane composition defines the pool of substrates available for conversion. Storage provides another pathway for dietary fat. When intake exceeds immediate structural and energetic needs, fatty acids are stored in specialized cells. This storage is not inert. It represents a reservoir that can be mobilized when conditions change. The composition of stored fat reflects dietary patterns and can influence the types of fatty acids released during periods of increased demand, affecting both energy production and signaling. Oxidation of fatty acids provides energy under conditions where they are directed toward mitochondrial pathways. This process depends on the ability of cells to transport fatty acids into mitochondria and maintain the conditions required for efficient oxidation. Structural factors influence this pathway by determining how easily fatty acids can be mobilized and delivered to the sites of oxidation. Dietary fat therefore becomes part of an integrated system where structure, signaling, storage, and energy production are interconnected. The body converts intake into components that are distributed and reassembled based on need, with membrane composition acting as a central determinant of how these components are used. Over time, the characteristics of dietary fat shape the structural and functional behavior of the system because they define the material from which membranes and signaling pathways are built. Digestion, emulsification, and transport. Dietary fat enters a system that cannot process it in bulk form. Lipids are hydrophobic and must be reorganized before they can cross aqueous environments and cellular boundaries. Digestion begins with mechanical dispersion and proceeds through chemical processes that reduce large lipid structures into smaller units that can be handled by enzymes. This transformation is not optional. Without it, fat remains inaccessible, passing through the system without integration. The process converts dense, aggregated material into dispersed particles that expose surface area, allowing enzymatic interaction to occur. Emulsification establishes this dispersion. Bile-derived molecules interact with dietary fat, breaking it into smaller droplets and stabilizing them within the intestinal lumen. These molecules orient themselves at the interface between lipid and water, preventing droplets from merging back into larger masses. This increases the effective surface area and creates a condition where enzymes can access lipid substrates. The efficiency of this step determines how completely dietary fat can be processed. Poor emulsification leaves large droplets intact, limiting enzyme activity and reducing absorption. Enzymatic digestion follows emulsification. Lipases act on the surface of these droplets, cleaving triglycerides into fatty acids and monoacylglycerols. This reaction is constrained by access. Enzymes cannot penetrate large lipid masses and depend on the interface created by emulsification. As digestion proceeds, products accumulate at the surface, and biocomponents maintain dispersion so that enzymes can continue to act. The rate of this process determines how much lipid is converted into absorbable units before it reaches the lower intestine. Absorption requires these products to cross the intestinal membrane. Fatty acids and monoacylglycerols move toward the enterocyte surface, where they are taken up and reassembled into new lipid structures within the cell. This step depends on membrane properties that allow controlled entry while maintaining separation from the lumen. Once inside, these components are reorganized into transport particles that can move through the body without aggregating or disrupting aqueous environments. Transport begins with the formation of these particles, which package lipids into a form compatible with circulation. They move through the lymphatic system before entering the bloodstream, bypassing immediate processing by the liver. This routing allows peripheral tissues to access dietary fat directly. The structure of these transport particles determines how they interact with cell membranes and how efficiently lipids can be delivered to tissues. Distribution depends on recognition and uptake mechanisms at target cells. Enzymes at the surface of blood vessels act on circulating particles, releasing fatty acids that can be taken up by nearby cells. This process is localized, linking delivery to the metabolic state of specific tissues. Membrane structure influences both the activity of these enzymes and the ability of cells to absorb released fatty acids. When structure supports these interactions, delivery is efficient and targeted. Residual components of transport particles are cleared and processed, completing the cycle. The system continuously breaks down, reassembles, and redistributes lipids, maintaining a flow of material that supports structural and energetic needs. Each step depends on maintaining interfaces between lipid and aqueous environments and on membrane conditions that allow controlled transfer across boundaries. Digestion, emulsification, and transport therefore form a sequence that converts dietary fat into usable components and directs them to where they are needed. The process relies on creating and maintaining interfaces that allow lipids to be processed without losing structural control. When these steps function efficiently, dietary fat is integrated into the system as both structural material and energy substrate. When they do not, access is reduced and downstream processes receive inconsistent input because the initial transformation and delivery of lipid components have been compromised. Lipoproteins as delivery systems. Lipoproteins function as transport structures that move hydrophobic lipids through an aqueous environment while preserving control over where and how those lipids are delivered. They are not passive carriers drifting through circulation. They are organized particles built with a lipid core and surface layer that allows interaction with cell membranes and enzymes. This structure enables them to carry triglycerides, cholesterol, and other lipids in a form that remains stable in blood while still being accessible for controlled transfer into tissues. The architecture of a lipoprotein defines its behavior. The core contains hydrophobic lipids that cannot exist freely in circulation. Surrounding this core is a surface composed of phospholipids, cholesterol, and proteins that orient toward the aqueous environment. These surface components determine how the particle interacts with receptors, enzymes, and other structures within the vascular system. Different classes of lipoproteins vary in size, composition, and function, reflecting their role in either delivering lipids to tissues or redistributing them for reuse. Delivery begins when lipoproteins encounter tissues that express the appropriate receptors or enzymatic activity. Enzymes located at the vascular surface act on circulating particles, releasing fatty acids from triglycerides. These fatty acids are then taken up by nearby cells. This process is spatially controlled. It occurs where metabolic demand or structural need signals for uptake. The lipoprotein does not decide where to deliver its contents. The receiving tissue defines the interaction through its membrane state and signaling profile. Cholesterol transport operates through similar interactions but follows a more regulated pathway. Cells express receptors that bind to specific lipoproteins and internalize them, bringing cholesterol into the cell. This uptake is driven by structural demand. Membranes that require reinforcement or remodeling increase receptor activity, pulling in more cholesterol. The process is responsive rather than excessive. It reflects the condition of the cell rather than the absolute concentration of lipoproteins in circulation. After delivering part of their contents, lipoproteins are remodeled. They shrink, change composition, and continue circulating, interacting with other tissues or returning to the liver for further processing. This continuous remodeling allows the same particle to participate in multiple delivery events, redistributing lipids across the system. The process maintains balance by ensuring that lipids are not confined to a single location but are available where needed. The interaction between lipoproteins and the vascular wall depends on endothelial membrane integrity. When the endothelial surface is stable, lipoproteins move through circulation with minimal retention, engaging only where delivery is required. Structural disruption alters this interaction. Increased permeability or changes in receptor behavior can lead to prolonged contact between lipoproteins and the vessel wall, reflecting local demand for lipid material rather than a failure of the transport system itself. Energy availability supports the processes that govern lipoprotein function. Receptor activity, particle remodeling, and intracellular processing all require ADP. Efficient mitochondrial membranes ensure that these processes occur continuously and with precision. Reduced energy supply limits the ability of cells to manage lipid delivery effectively, altering distribution patterns across tissues. Lipoproteins therefore act as delivery systems that integrate transport with structural demand. Their design allows lipids to move through the bloodstream without disrupting the environment while remaining accessible for targeted uptake. The distribution of their contents is determined by membrane conditions at the tissue level, ensuring that lipids are directed toward areas that require them for structural maintenance, signaling, or energy production. Incorporation into membranes over time. Membrane composition is not fixed. It is continuously remodeled through the gradual incorporation of fatty acids derived from circulation, replacing existing components as membranes are repaired, expanded, or turned over. This process occurs at a pace defined by cellular activity and structural demand, not by immediate intake. Dietary fat enters the system, is distributed, and then becomes available as a substrate for membrane synthesis. Over time, repeated exposure to specific fatty acid profiles shifts the composition of membranes across tissues, altering their physical and functional properties in a cumulative manner. Incorporation begins with the integration of fatty acids into phospholipids and other structural lipids within the cell. This requires enzymatic processes that assemble these components into the bilayer, positioning them according to the needs of the membrane. The selection of fatty acids is influenced by availability and by the requirements of a local membrane environment. Cells under mechanical or signaling stress may preferentially incorporate components that increase stability or adjust fluidity, aligning membrane properties with functional demands. Turnover ensures that this incorporation is continuous. Membranes experience constant wear from mechanical forces, signaling events, and metabolic activity. Damaged or outdated components are removed and replaced with newly synthesized lipids. This replacement is not random. It reflects both the composition of available substrates and the conditions within the cell. Over time, this leads to a gradual shift where the characteristics of incoming fatty acids become embedded in the structure of the membrane. The effects of this process are distributed across different cellular compartments. Plasma membranes, organelle membranes, and specialized structures, such as synapses or mitochondrial membranes, each incorporate lipids according to their specific requirements. Differences in composition between these compartments influence how each performs its function. Changes in input therefore produce distinct effects depending on where incorporation occurs, but the underlying mechanism remains the same. Membrane properties emerge from this composition. Packing density, permeability, and the ability to support protein function depend on the types of fatty acids present. As incorporation proceeds over time, these properties adjust. This alters how receptors behave, how ions move across the membrane, and how signals are transmitted within the cell. These changes are not abrupt. They accumulate gradually, reflecting the ongoing replacement of membrane components. Storage pools contribute to this process by providing a reservoir of fatty acids that can be mobilized when needed. The composition of these stores reflects prior intake and influences the types of fatty acids available for incorporation during periods of increased demand. This creates a link between past dietary patterns and current membrane structure, as stored lipids are drawn upon to support ongoing remodeling. Energy availability determines the rate at which incorporation and turnover can occur. Synthesis of membrane components and their integration into existing structures require ADP and coordinated enzymatic activity. Efficient mitochondrial function supports this process, allowing membranes to be maintained and adapted as conditions change. Reduced energy supply slows turnover, prolonging the presence of existing components and limiting the system's ability to adjust composition. Incorporation into membranes over time, therefore, represents a continuous restructuring of the body's boundaries based on available lipid inputs. The process integrates dietary fat into the architecture of cells, shaping membrane behavior across tissues. As new components replace old ones, the physical and functional characteristics of membranes shift, influencing how the system responds to mechanical forces, signaling inputs, and metabolic demands, because the structure that governs these processes is being rebuilt incrementally. Remodeling cycles and turnover. Membranes exist in a constant cycle of breakdown and reconstruction that maintains their functional state under continuous stress. This cycle is not occasional maintenance. It is a continuous process that replaces components as they are altered by mechanical force, signaling activity, and metabolic reactions. Lipids within the bilayer are subject to oxidation, enzymatic modification, and physical deformation, all of which change their behavior within the membrane. Turnover removes these altered components and replaces them with newly assembled lipids, preserving the structural conditions required for controlled permeability, signaling, and electrical stability. Breakdown begins when membrane components are identified as no longer suitable for maintaining function. Enzymatic activity targets specific lipids, cleaving them from the bilayer and converting them into intermediates that can be reused or further processed. This removal is selective. It reflects local conditions such as stress, damage, or changes in signaling demand. The rate of breakdown increases when membranes are exposed to higher levels of mechanical or chemical stress, accelerating the need for replacement. Reconstruction follows immediately through the synthesis and insertion of new lipids. Fatty acids from circulation or local stores are activated and assembled into phospholipids that match the requirements of the membrane. This assembly occurs within the cell and is directed toward membranes that require reinforcement or modification. The integration of new components must align with existing structure, maintaining continuity while adjusting composition. This requires coordinated activity between synthesis pathways and membrane insertion mechanisms. Cycles of remodeling differ across cellular compartments. Membranes that experience rapid signaling or high mechanical load, such as neuronal synapses or vascular endothelium, undergo faster turnover than more stable structures. This variation reflects functional demand. Areas that rely on precise signaling or structural integrity must maintain tighter control over membrane composition, requiring more frequent replacement of components that drift from optimal conditions. Turnover also interacts with signaling processes. Breakdown of membrane lipids generates intermediates that can act as signaling molecules, linking structural maintenance to cellular communication. This creates a feedback system where increased signaling activity can accelerate remodeling, and remodeling can influence the signaling environment. The balance between these processes determines whether the system maintains stability or shifts toward a state of persistent activation. Storage pools provide material for reconstruction during periods of increased demand. Fatty acids stored in specialized cells or within the cell itself are mobilized and directed toward membrane synthesis when turnover rates rise. The composition of these stores influences the characteristics of the newly formed membrane, linking past inputs to current structural outcomes. Energy supply constrains the entire cycle. Both breakdown and reconstruction require ADP to support enzymatic activity, transport, and synthesis. Efficient mitochondrial function ensures that turnover can proceed at a rate that matches demand. When energy availability is reduced, turnover slows, allowing altered or damaged components to persist within the membrane. This reduces structural consistency and affects downstream processes that depend on membrane integrity. Remodeling cycles and turnover, therefore, maintain the structural framework that supports cellular function. By continuously replacing components, the system preserves the conditions required for controlled exchange, signaling, and energy production. When these cycles operate efficiently, membranes remain aligned with functional demand. When they are disrupted or slowed, structural drift accumulates, and the system begins to operate with components that no longer support optimal behavior because the process that enforces structural renewal is no longer keeping pace with the forces that degrade it.